You know, we all face problems where we have way too many choices and not enough time or resources to handle them. Today, we're going to look at a classic puzzle that surprisingly gives us a really elegant blueprint for how to solve problems just like that. Let's dive in.
Okay, so imagine you're packing for a trip. You've got a bunch of items laid out, and each one has its own value to you, and of course, its own weight. But here's the catch. Your bag has a really strict weight limit. So how do you decide what to bring to get the absolute most value without going over that limit?
Well, this little puzzle actually has a formal name. It's called the 0-1 Knapsack Problem. Now, that 0-1 part is super important. For every single item, you have a simple binary choice. You either take it, that's a 1, or you leave it behind, that's a 0. You can't just take half of your laptop, right? It's all or nothing. And the whole goal is to make the total value of what you pack as high as it can possibly be.
Now you might be thinking, okay, that sounds pretty simple. I'll just pick the most valuable stuff first. But as we're about to see, our first instinct, our gut feeling, can sometimes get it wrong.
This is what computer scientists call a greedy approach. You just grab the item with the best value to weight ratio first. But look, that can be a real trap. Sometimes that single best item is so heavy, it takes up so much space that it stops you from packing a handful of other items that, when you add them all up, would actually be way more valuable. The best solution isn't always the most obvious one.
All right, so if the greedy approach doesn't always work, what's the alternative? You might think, well, why don't we just check every single possible combination of items? And, well, that leads us to a completely different kind of problem, a much, much bigger one.
Let's start small. Say you've only got 2 items. You've got 4 choices, right? You can take none of them, take the first one, take the second one, or take both. Easy enough.
Okay, let's double that to 4 items. Now the number of combinations jumps up to 16. It's growing, sure, but it still feels kind of manageable. You could probably write them all down if you had to.
But what if we have just 30 items? Suddenly, you're looking at over 1 billion possible combinations. A modern computer trying to check every single one of those would be running for a very, very long time. This is what's known as a combinatorial explosion. The problem's complexity just skyrockets.
This type of problem actually belongs to a special class of problems called NP-complete. And as this quote suggests, trying to find a perfect, fast solution is often just a fruitless search. It forces us to stop trying to check everything and instead to start thinking about how to search smarter. So how do we actually do that? How do we solve it? Well, let's imagine we have a secret from a clever gardener. Instead of using brute force, we're going to use this really elegant technique called branch and bound. I want you to picture every possible combination of items as a branch on a giant, sprawling tree. The root of the tree, that's your empty knapsack. And with each level you go down, you make a choice about a new item. Are you going to take it, or are you going to leave it? Our goal is to find that one single branch that leads to the most valuable collection of fruit, without having to climb along every single one.
So the gardener's method is actually pretty simple. First, you branch out. You just start down a path, making a series of choices. Then, and this is the crucial part, at each step you bound. You basically calculate an optimistic guess, the best possible outcome you could get if you keep going down this path.
And here's where the magic happens. If you're exploring a branch and you realize that its absolute best-case scenario is still worse than a complete solution you've already found somewhere else on the tree, you just stop. You prune that entire section of the tree. You don't waste any more time on it because you know for a fact the best answer can't possibly be down there. So pruning helps us avoid obvious dead ends. That's a huge step. But to be really efficient, we also need a guide, right? We need a way to decide which of the paths we haven't explored yet is the most promising one to check out next. See, a blind search would just explore the tree in a fixed order, maybe always going down the leftmost branches first. But an intelligent search is different. It pauses, it looks at all of its available unexplored paths, and it always chooses to investigate the one that looks the most promising at that moment. This strategy is called least cost search, or LC search for short. At every step, it looks at all the open possibilities, the frontiers of our search, and it always chooses to continue down the path that holds the most potential value. It's kind of like our gardener always walking towards the part of the orchard that smells the sweetest. Okay, so we have our key ideas. We're branching out, we're bounding our search by pruning bad paths, and we're using LF search to guide us. Now, let's watch how they all work together. This diagram really shows the whole process beautifully. The algorithm starts at the top, at the root. It explores its first 2 options, nodes 2 and 3.
It sees that path 2 has a better potential outcome, a better estimate, so it explores that one next. It keeps expanding whichever node looks the most promising. But look over at node 7. It's marked with a K for killed. That means the algorithm realized its best-case scenario wasn't good enough to beat a solution it had already found, so it was just pruned. This process continues, intelligently navigating this massive tree of choices instead of getting lost in it.
Now, there's one small but really clever little detail here. The algorithm is called least cost because it's built to find the lowest cost. So, to make it work for our problem, we just turn our profits into negative numbers. That way, finding the biggest profit is exactly the same as finding the lowest or most negative cost. It's just a neat little math trick that lets this powerful search tool solve our exact problem.
So, what this all comes down to is a really powerful way of thinking. When a problem has way too many choices, we don't have to check them all. We can map them out like a tree, use smart estimates to prune the branches that are dead ends, and use an intelligent guide like least cost search to always explore the most promising paths first.
In the end, the lesson of the knapsack problem isn't really about packing a bag. It's this beautiful metaphor for how we can solve complex problems in our own lives. It teaches us that sometimes the most powerful tool we have isn't more power, but more wisdom. The wisdom to know where not to look. The goal isn't to exhaust every single possibility, but simply to learn how to search intelligently.